All right, so let's get started. In this chapter, we are going to talk about electromagnetic induction. This chapter is probably one of the most conceptual chapters in this entire course, so I would recommend that you pay attention and make sure you're fully understanding everything. Feel free to utilize the office hours to ask me any questions that you have. Okay, so before we get started with the material of this chapter, we'll just review a few concepts from before. The first is the concept of magnetic flux. So, what is magnetic flux? So, you should know that we've talked about flux a lot in our lectures in class. So, magnetic flux uh, represents the number of magnetic field lines that are passing through any surface. So, the flux of the magnetic field over a certain surface is simply the number of magnetic field lines that are passing through that surface. Mathematically, it can be expressed as flux phi is equal to surface integral B dot ds. Okay, so if the magnetic field B is constant over a certain area A, then the flux is given by, then the surface integral just becomes B dot A, the dot product of B and A, right? And this should be fairly uh, familiar to all of you by now. We have seen it in the case of magnetic fields, electric fields. All right, so that is the magnetic flux, and what it measures is the number of field lines passing through the area. Okay, now another thing that we are going to revisit is the definition of EMF. So we had in chapter 25, we had defined EMF as the work done by the non-electrostatic forces in moving a unit positive charge from the negative to the positive terminal of the EMF device, which was usually the battery. We are now going to define EMF as the total amount of work done by all forces in the circuit. They could be electric, magnetic, any kind of force in the circuit, in moving a unit positive charge in a complete loop around the circuit. Okay, so let's see what this definition is. And also, I'm going to show you now that these two definitions are identical. So let's just go to the Word document. So here is how I defined EMF back in chapter 25. Here is a battery. The battery has a positive end, a positive terminal and a negative terminal. Okay, and suppose I connect the battery to a circuit. The moment you make that connection, what happens? You have a bunch of electric fields established throughout the circuit. So the electric fields look like this. All right, and inside the battery, the electric fields are going to look like this. Remember, the electric fields always point from positive charges to negative charges. Okay, now if you consider a positive charge, remember that in a circuit made up of metal wires, you really don't have positive charges. You have electrons moving in the opposite direction. But we are just going to consider a fictitious positive charge. So if you consider a fictitious positive charge, the electric fields are going to drive it from the positive end of the battery through the resistor back to the negative end of the battery. And that would be the end of the story as far as the electric fields are concerned. So something needs to drag this positive charge from the negative end of the battery back to the positive end of the battery. And that is done by non-electrostatic forces, which push on the charge in the opposite direction and bring it from the negative end of the battery to the positive end of the battery, right? So the work done, so the first definition of EMF was the work done by these non-electrostatic forces. NES just means non-electrostatic forces in moving a unit positive per unit charge, in moving the charge from the positive end to the negative end of the battery. I'm just writing that as the work done by the non-electrostatic forces in moving the charge Work done per unit charge by non-electrostatic forces in moving the charges from the negative to the positive end of the battery, right? Okay, now I'm coming up with a new definition of EMF. So this is the old definition from chapter 25. The new definition of EMF is the following. It's the work done by all forces. So I'm going to write that as the total amount of work done by all the forces in moving unit charge in a complete loop, one complete loop. So suppose the charge starts over here at point A. What is the work done by all the forces acting on it in moving the charge in a complete loop from A back to the point A? So I'm going to write that as loop. And this is the work done per unit charge. So I'm dividing this by Q. This is our new definition of EMF, right? So at first you might think that these two definitions sound pretty different, but you can prove that this new definition is equivalent to the old definition. If you think about it a little bit, you can prove it yourself. I'll just demonstrate that for you. So let's think about the total amount of work done in this particular circuit. Let's think about the total amount of work done by all the different forces. Now there are only two types of forces here, the electrostatic forces and the non-electrostatic forces. So EMF, according to the new definition, was W total over the entire loop over Q. W total over the entire loop can be written as W non-electrostatic over the loop plus the work done by the electrostatic forces, which is just the work done by the electric fields over the loop, divided by Q. All right. Now, the work done by the non-electrostatic forces over the loop, remember that there's no non-electrostatic forces outside the battery. So all the non-electrostatic forces are inside the battery, right? So this is really just the work done by non-electrostatic forces inside the battery, because there's no question of non-electrostatic forces outside the battery. What about the second quantity over here? That's the work done by the electric field in going over a complete loop, right? Now the force due to an electric field. So if you have an electric field E and it's acting on a charge Q, in class I would ask you this question again, like I ask you in every class. What is the force on charge Q subjected to an electric field E? The answer should be Q times E, right? So this is going to be, the force is going to be QE, and work, as you know, is the line integral of force. So it would be the line integral of QE dot TL, and over a complete loop, I could just write loop here, or I could just use the more fancy mathematical notation. When you come back to the same point where you started in a line integral, you denote that by putting a circle through the integration sign, right? Okay, so that's the numerator. The whole thing is divided by Q. All right, now so the first term becomes WNES, battery, divided by Q. And in the second term, the Q cancels out and you get line integral E dot dl. We have discussed many times earlier that line integral E dot dl is just 0 for static electric fields. And so we end up getting the same thing as the previous definition. So same thing as this, right? So the two definitions give you exactly the same result for the kinds of circuits that we've seen so far. Okay. All right, so that is all the review I wanted to do. There's just one other thing that I should also review. It's not on the PowerPoint, but I should quickly go over it now. Suppose you have a loop of wire and it's carrying a current, right? Obviously, there must be some battery or something, which I'm not drawing here, but just imagine that the current is moving through, moving in a circular loop. You know that this will produce a magnetic field. What is the direction of the magnetic field going to be? So we've talked about this in class and also in my previous videos. To find the direction of the magnetic field, you would curl the fingers of your right hand in the direction of the current, and your thumb will point in the direction of the magnetic field. So if I do that over here, I find that for the current moving clockwise, the magnetic field points into the board, right? Or into the page. So in this case, the magnetic field would be into the page. All right, so that, and then if the current were moving in the counterclockwise direction, the magnetic field would be out of the page. Okay, so that's a fact that we're going to use in today's lecture. All right, so now let's move on to the concept of induced EMF. So far we've seen that in order to make a current flow through a circuit, you have to have some sort of EMF device. So it has to be a battery or a solar cell or some kind of EMF device, right? Can you have a current flowing through a circuit with no battery? If you ask this question in the middle 1800s, people would have said no. I mean, that would be a completely ridiculous thing. How can a current flow without a source of EMF? But it was discovered by Faraday and also somebody else, I've forgotten who it was, roughly the same time, that you can make a current flow through a circuit without a battery under certain circumstances. And this is completely spooky. Essentially, you can use a magnet to make current flow through a circuit without any battery. So I'll first demonstrate this to you, and let me just quickly demonstrate this to you first. Okay, so this guy has an ammeter, and he's connecting this ammeter to a coil or several turns, a coil made up of several turns of wire, right? And we'll see what happens. So he has different coils here. The first one on the left is one loop. The second one is 10 loops, I think. And the third one has multiple loops. So he's going to connect these coils to a circuit, right? And there is no battery or anything. And he's going to use this magnet. So here he has connected the coil to the circuit. You don't see much of, if you look carefully, you'll see that there is a slight deflection here as he moves the magnet in and out of the coil, but you can't really see it, right? However, if you do it with the coil which has 10 turns, do the same thing. If you just move the magnet back and forth, amazingly, there is a current flowing through this coil. Where did that current come from? There is no battery or anything, so how can you possibly have a current in this case? And you can also notice that if he moves the magnet faster, the current flows, you have more current flowing through it. If he holds the magnet still, nothing happens. It's only while the magnet is moving back and forth that you have a current flowing, right? Okay, I wish I could have done this demonstration for you. It's really fun to show. Yeah, he's making the point that if you just hold it in there, still nothing happens. All right, now he's going to try the third coil, which has 100 turns. Now notice how much current flows this time. A lot more current flows as he moves the magnet in or out of the coil, right? So having a lot of turns seems to help. It produces more current. Okay, so you should watch the full video. It's a nice video. He explains this pretty nicely. So Faraday did a bunch of experiments of this sort. And here is a summary on the slide. Here is a summary of the things that he noticed. He noticed that the magnetic field, that a current flows through a loop. Or in other words, an EMF is induced in the loop if A, the magnetic field over the loop is changed, either by moving the loop or the magnet, or by changing the magnetic field of the magnet. So this would have also happened if we were just holding the magnet still and just changing the magnetic field by, like maybe it's an electromagnet, so he can increase the current through it and make the magnetic field stronger. So if you can either move the magnet around, or you can just change the strength of the magnet and everything is still, or you can do both. That would make a current flow. Then you can increase the area of the loop, decrease the area of the loop, that would make a current flow. You can change the orientation of the loop, so you can turn the loop around inside the magnetic field without changing its area or without changing the magnetic field. That would also make a current flow through the loop, right? And these things are, I found another video here, which is this fourth bullet point, and you should watch that at some point. So this video also shows you some more of those effects. Now notice that the current only flows while the change is happening, and the current is stronger when the change happens faster. So you get more of an effect if you make that change really quick. And you notice that when I showed you the first video and he moved the magnet in very quickly, that's when you got more of a deflection in the needle. If you move the magnet in slowly, you didn't get that much of a deflection, right? So Faraday did a bunch of experiments like this, and then he asked himself the following top hat question. Okay, yeah, he asked himself this question. It would have been a top hat question for you, but I guess we'll just have to do it without top hat. So see if you can answer this question before you move on. Faraday asked himself the same question, and he of course didn't have the benefit of multiple choice, but let's see if you can figure it out with the benefit of multiple choice. So the question is that, what is the common thread among all these experiments that we just discussed? What is the thing that changes in each experiment, causing a current to flow through the loop? The correct answer is that each of these experiments involves a change in the number of magnetic field lines penetrating the loop, right? A is not correct because each experiment involves a change in magnetic field. You can have the magnetic field constant, but if you move the loop around or if you change the orientation or the area of the loop, you're going to get a current. So A is not correct. B says that each experiment involves relative motion between the loop and the magnet. That's also not true. I told you that you can hold the loop and the magnet still, but if you vary the magnetic field, if you alter the magnetic field of the magnet, that would cause a current to flow. C is not correct because change in the area of the loop would cause a current to flow, but it's not the only thing that happens. It's not the only thing that does that. Each experiment involves a change in the orientation of the loop, not true for the same reason. So the correct answer is that each experiment involves a change in the number of magnetic field lines penetrating the loop. Okay. So we therefore conclude that an EMF, and hence current, is induced only while the number of magnetic field lines penetrating the loop changes. In other words, you have an EMF whenever you change the flux of the magnetic field line over the loop, right? So because the number of field lines is measured by the flux. So you get an EMF when the flux of the magnetic field over the loop changes. All right. Okay. So now we are going to talk about what is called the flux rule, which quantifies how much EMF is going to be produced when you make a change in the flux of the magnetic field, right? What Faraday found out was that the EMF produced is proportional to the rate of change of flux, right? And so you can write that the EMF is equal to d phi b dt. And let me write that down. Induced EMF, let's get rid of this, is equal to d phi b dt. the rate of change of flux. There is a negative sign which is put here, and I'm going to explain what that is in a moment. So this is for a coil with a single turn. If you've got n turns or n loops in your coil, then the EMF is equal to minus n d phi b dt. It's like n copies of that EMF is produced, one for each turn, right? So this is true this is the induced EMF for n loops. Okay, now what is this minus sign? The minus sign indicates the direction of the induced EMF, and it is given by, something called Lenz's law. So this quantity is called, called the flux rule. This equation is called the flux rule. The direction of the induced EMF is given by something called Lenz's law, and this minus sign is really due to Lenz's law. Now, there is a way of using this minus sign in doing calculations and problems, but I'm going to show you a simpler way of figuring out the direction of the induced EMF, and we will end up never actually using this minus sign. So what we're going to do in problems is we will always do the magnitude of the EMF is equal to n d phi b dt. And so that's why, since we are taking the magnitude of the EMF, we are not considering the minus sign. We will rarely ever need to use this minus sign, because I'm going to show you a different method of figuring out the direction of the induced EMF. So let's talk about that now. Direction of induced EMF. Okay, suppose I have a loop of wire. Okay, I've got this loop of wire. It's not connected to any battery or anything. It's just a simple loop of wire, right? Suppose I bring a magnet closer to this loop of wire. So let me first show you what the scenario is, what we are doing, and then I'll draw a top-down view of it. So I have this loop of wire, and I'm bringing this magnet. I'm holding this magnet over here, and then I'm bringing this magnet. I rapidly bring this magnet close to the loop of wire. So this is before. And this is after. Okay, so you know that if the magnet is sitting still, there won't be any induced EMF. And then when I've brought the magnet to a rest afterwards, closer to the loop, there again won't be any induced EMF. But while I'm in the process of bringing the magnet in, I will see a current flowing through the loop, right? Let's imagine that we are viewing this from above. So let's imagine that our eye is somewhere over here, and we are watching this happen. So let's draw the view. Just imagine that the magnet is in front of the loop. I'm not able to draw it now. The magnet is in front of the loop, held perpendicular to the loop, and it's basically between your eye and the loop, right? And the north pole is facing the loop, the south pole is facing you, and all of a sudden you bring the magnet really close to the loop, right? Okay, so what did the magnetic field look like before you move the magnet? So the north pole of your magnet was facing the loop, right? So there were magnetic field lines going into the loop like this. I'm not drawing all of them. They'll again loop back and come to the south pole. I'm not drawing that. So you had magnetic field lines going into the loop. So from our top view, so this is the side view, and this is the front view of the same thing. So the magnetic field lines would be going into the page in that case, right? So I'll draw them as X's. The magnet was far away from the loop, so the magnetic field line is not that, there's not that many magnetic field lines. The magnetic field is not very strong. So this is the before. And afterwards, as you move the magnet very close to the loop, the magnetic field is much stronger because the magnet is now closer to the loop. So coming back over here, you have a much stronger magnetic field, plenty of field lines going through the loop. Okay, I should draw some arrows. Okay, so the magnetic field has become a lot stronger. Now think about what is happening from the point of view of the loop. So the loop sees that there is a certain magnetic flux which is increasing, that there's a certain magnetic flux caused by a magnetic field pointed into the page which is increasing, right? Remember that the loop is something that hits any kind of change. So the loop is going to do everything that it possibly can to oppose this change from happening, right? So it sees the magnetic flux increasing, and the magnetic flux is due to a magnetic field pointed into the page. Sees that flux increasing, it's going to try to counteract that increase in flux using its own little magnetic field. So which direction does it need to send its own magnetic field in order to cancel out the increase in flux? It obviously needs to create a magnetic field which is pointed out of the page in order to counteract the increasing magnetic field pointed into the page, right? So to cancel out it won't really cancel out the flux, but it will counteract the increase. To counteract the increasing flux, caused by a magnetic field pointed into the page, the loop will create its own the loop will create a magnetic field pointed out of the page, right? So in what direction does it need to drive a current in order to produce that magnetic field? Obviously, in order to drive a magnetic field pointed out of the page, the loop will need to send a current in the counterclockwise direction. So the EMF produced, and hence the current, produced in the counterclockwise direction. And so that is how you find out the direction of the EMF. Remember that the loop does not like any change, right? Any change of flux. So if it sees a flux decreasing, it will try to use its own magnetic field to help the dying flux. If it sees a flux increasing, it will try to use its own little magnetic field to try to cancel out that increasing flux. I mean, it doesn't succeed, of course, but it tries to cancel out, it does what it can to cancel out the increasing flux. So the loop is going to do everything in its power, which is basically all that it has in its power is just creating an EMF in either clockwise or counterclockwise direction. So it will produce an EMF in the counterclockwise or clockwise direction in order to cancel out the increasing or decreasing flux. I should say changing flux. And so that is how Lenz's law tells you the direction of the induced EMF. Right? Okay, just for completeness, I will do one more example. So let's just say that you have another loop of wire. And let's say that this time you have a magnet, which is, so I'll just draw the side view first. Let's say that you've got a south pole here and a north pole here. We are viewing it from over here as usual. And what you're doing is you're holding the south pole pretty close. And so now you're moving the magnet away from the loop, right? So what do the magnetic field lines look like? I'm not drawing all of them. I'm just drawing the part that goes through the loop. So the magnetic field lines, more or less, so they enter the magnet near the south pole, right? So the magnetic field lines look like this. And then when you move the magnet away, the diagram will look like this. The magnet is now far away. I should probably draw a few more over here, because the magnetic field will be stronger when the magnet is closer. So now you've moved the magnet away, and so the magnetic field will be weaker, but again pointing in the direction of the magnet. Okay, so the question is, which direction will the EMF be produced from the perspective of the eye of the person viewing? And the person viewing is over here. All right, so you should try this on your own. You should pause the video and try this on your own and see if you can figure it out. So here is the loop. We are asking from your perspective, you're the person viewing. Suppose a magnet was held near the loop with its south pole closer to the loop, and then you suddenly pull the magnet away, so it's closer to you and away from the magnet, away from the loop. What is the direction of the induced EMF going to be? So see if you can figure it out yourself. Pause the video and try to get an answer yourself. Once you've figured it out, here is how I would approach it. So initially, the magnetic field looked like this. Let me just move this diagram over here. Initially, the magnetic field over the loop looked like this. The magnetic field lines were coming out of the page, and they were strong. Okay, and finally, once you've moved the magnet away, the magnetic field lines look like this, because the magnetic field is weaker, right? So from the perspective of the loop, what the loop is saying is that there is a magnetic flux caused by field lines coming out of the page, which is getting weaker. The loop wants to fight the change. So it will use its own magnetic field to try to help the dying magnetic field, right? And it needs to point its own magnetic field lines in the direction of the dying magnetic field, because it's trying to help it. And so it will have to point its own magnetic field, out of the page. That makes sense? It's trying to help the dying magnetic field because it does not like the change of flux. So in order to produce a magnetic field out of the page, the loop will have to drive a current, according to the right-hand rule, in the counterclockwise direction. So the answer is that the EMF and the current will be produced in the counterclockwise direction. For this example. So please make sure you understand this. In the PowerPoint, I have a couple of other examples which you can try on your own. So I think this is very similar to the example that we just did. And I have a top hat question, which is again quite similar to that. Okay, so please make sure you understand how to calculate the direction of the current, because this is going to be very, very useful in the next couple of chapters. All right. Now, the next few slides are a couple of applications of the flux rule. E is equal to minus d phi b dt. In general, you can have two types of problems. I mean, two types of ways you could conceivably use this. One is that so typically in the problems, oops, typically in the problems, you're asked to calculate the induced EMF, and the induced EMF happens only because the flux is changing, right? Now the flux depends on the magnetic field, it depends on the area, it also depends on the orientation of the angle between the area vector and the magnetic field vector, or in other words, the orientation of the area relative to the magnetic field, right? It depends on all three of these quantities. So the flux can change in many different ways, right? So all you have to do is figure out how express the flux as a function of these quantities. And remember that the induced EMF is nothing but, the magnitude of the induced EMF is nothing but the derivative of the flux with respect to time. So it might happen that the magnetic field is changing, so B is a function of time, and then you take a derivative of that, right? Or A is a function of time, and then you take a derivative of that. Or even theta might be a function of time, so the loop might be rotating, and so you just express the flux as a function of time, and then you just go ahead and take its derivative, and that gives you the EMF. In certain problems, you might have a situation like this, and that's the problem on the PowerPoint, the first problem on the PowerPoint. So I'll let you try this problem yourself, and I think it's also fully worked out in the slide. But basically what's happening, if I remember correctly, is that you have a uniform magnetic field, and then you have a loop inside this magnetic field, and that loop is rapidly, the magnet is suddenly moved away. So the magnetic field, you're not given the magnetic field as a function of time, but you can easily figure out the change in the magnetic field. So essentially you can get an approximate value of EMF by just doing delta phi divided by delta t. So in some problems you might be able to take a derivative and get an exact value for the EMF, or you might just have enough information to do a delta phi divided by delta t, right? And this will be pretty close to the derivative if the delta t is small. All right, so I'll let you look at this problem on your own. This problem I think is very similar. Okay, let's try this problem. So I'll let you think about this problem first. So please pause the video and see if you can work this problem out, and then we will talk about it. Okay, I think there are two versions of this problem. All right, so let's look at this one first. So it says that an L-shaped conductor moves at a uniform velocity, constant velocity across a stationary L-shaped conductor in a uniform and constant magnetic field. The conductors have resistance per unit length R ohms per meter. What is the direction of the induced current, right? So what's happening here is that the one of these L-shaped conductors, the one on the right, is moving diagonally, right? And so the area formed, the square area formed by these two L-shaped objects is increasing in size, because this conductor a little while later will be somewhere over here. So the area of this square loop is increasing, right? And the question is, what is the direction of the induced EMF and the induced current? So how would you do that? So as far as the loop is concerned, it sees that a flux over it, the flux of the magnetic field over it, caused by a magnetic field pointed out of the page, is increasing, right? The loop will try its best to fight any change. So what it's going to do is, it will try to cancel out some magnetic field. So the magnetic field that it will produce will have to be into the page. Sorry, did I say that correctly? So I'll say it again. So the loop sees that there is a magnetic field pointed out of the page. The dots mean out of the page, and the flux of that is increasing because the area of the loop is increasing. Remember that flux depends on the magnetic field, the area, and theta, right? So here the A is increasing, and so the flux is increasing, and the loop's goal right now is to cancel out that increase of flux, counteract that increase of flux. So in order to counteract the increase of flux, the loop will try to send a current in the counterclockwise direction, in the clockwise direction, like this, what is the direction of the magnetic field that would produce? That would produce a magnetic field pointed into the page, right? And that will cancel out the increase in flux. So I hope that's clear. And I'll just say this one more time for the people who are learning it for the first time. So the first thing that we notice is that there's a flux due to a magnetic field pointed out of the page, which is increasing. The loop tries its best to fight that, and so it produces a magnetic field pointed into the page, right, by driving an EMF in the clockwise direction. So I hope that was clear. The correct answer is that the current will flow clockwise. Okay. There's a second part of this problem where it asks you what is the magnitude of the induced EMF, right? So we've already figured out the direction of the induced EMF using Lenz's law. What is the magnitude of the induced EMF? So let's see how we would do that. Let me just find that problem over here on my big screen. Okay, all right. So what's happening here is that we have this L-shaped object, and this is moving with a velocity v, right? Okay, so our entire goal here is to express the flux as some function of time. That's what we want to do, because the EMF, the magnitude of the EMF is equal to n times d phi b dt. So if we can express the flux phi as a function of time, we can take its derivative with respect to time and we have the answer, right? So let's see how we can express the flux as a function of time. In this case, the flux is changing. So normally the flux depends on three things. It's a function of the magnetic field, it's a function of the area of the loop, it also depends on theta, right? So in this case, it's A which is causing the flux to increase. So let's try to express the flux as a function of area, right? I mean as a function of time. So what is the flux going to be? If the area is flat and the magnetic field is uniform, then we know that the flux is simply B times A, which this A is a function of time, B dot A. That's what it is, right? Simple formula for flux. And the dot product here will just be B multiplied by A. And I'm just writing A of t painstakingly, just because we are going to express A as a function of time in a moment. Cosine of 0. We can take the normal to the area to be in the same direction as the magnetic field. So that's just going to be B multiplied by A as a function of time. So that's our phi as a function of time. Now let's express this area as a function of time. To do that, there's multiple ways you can do it, but probably the easiest way would be to just work with the diagonal here. So what is the length of this diagonal at time t, after t seconds, right? Let's say that t was 0 when this corner and this corner were coinciding and the area was 0. So after t seconds, what is the length of the diagonal? Clearly, it's just going to be v multiplied by t because it's moving at a constant velocity. So each side of the triangle would be vt divided by root 2. I mean, each side of the square would be vt divided by root 2, right? Just Pythagoras theorem. So let's plug that in. So what's the area going to be? So the area is just going to be vt divided by root 2 squared, right? So that's v squared t squared divided by 2. That's A as a function of time. Let's plug that in and we are done. So B times v squared t squared divided by 2 is our phi as a function of time. And so from here we can find the magnitude of the induced EMF. And I'm putting these absolute value signs because I don't really need Lenz's law, so I don't really need the minus sign here. I've already figured out the direction of the EMF. D phi dt. Sometimes I like to write phi sub b dt to indicate that it's the flux of the magnetic field, but here it's pretty obvious that it's the flux of the magnetic field. So you just take a derivative of this, which is going to be bv square t, and the 2 cancels out, and that's the answer. So B is the correct answer choice, right? And we've already figured out the direction of the magnetic field. So hopefully this problem and the last one makes it clear how to approach these problems. What you do is you choose you can figure out the direction of the magnetic direction of the EMF using Lenz's law, right? And then you find the magnitude of the EMF using the flux rule. E is equal to d phi dt.